Yeah, so today I'll be just giving a quick intro to SGX, and then what we're building here are the new oracles that are, in a way, like we're having a solution that's has this like heavy reliance on SGX. But yeah, let's get started. So what is SGX? This is a very philosophical question as well. So SGX is a form of trusted execution environment for TEs, right? Basically, TEs are just like you have this kind of like secure area in your main processors, right? And then it can guarantee that the code and data being loaded into your processor is protected against like a malicious host that can potentially have like, administrative privileges, right? So for example, for your operating systems, for your hypervisors, right? For your BIOS, for your firmware, for your SMMs, and then for any form of remote attacks, right? Even if like a lot of these like malicious administrators want to do potential attacks against like whatever program you're running in the enclaves, right? At least this is what Intel is promising, right? You're having a much smaller attack surface here, right? You have some side channels here, you have this like interface towards hardware, but then you're basically relieving from the potential attack surfaces you can have for the OS and the VMMs. And then, of course, right, for whatever code you're running in the enclaves, right, you have confidentiality and the integrity both being guaranteed, right? This is also kind of like the two core features. That's the basis of Andrew and Phil's talks, right? Like when you're running your enclave-based auctions or your private contracts, right? You need to make sure that the programs are being executed with integrity. And then, of course, there's like a privacy element to that as well. So the core components of SGX we're listening for here, there's much more than this, but then due to the time constraints we have, so TCP or trusted computing base, you can think of this as a measurement basically that's made on all the security parameters of the underlying hardware, right? So this is used for a lot of like key generation and then like attestation creation as well. Yeah, and then so hardware secrets, we have the root provisioning key and then the root sealing key. The provisioning key is, so basically Intel has this like huge registry of all these RPKs that they would use to basically verify, say, a particular enclave is being produced or manufactured by them or not. The RSK, they're claiming that this is something that they do not know, right? So this is being hard-coded in the hardware when it's being produced, but then Intel has basically eliminated all the traces for production for the RSKs. So this is used more in actual production for like a key generation and then like for the sealing process that Andrew was telling about as well. Remote attestation, this is kind of like a core component of SGX that makes it very powerful. And then there's also like the differentiation with, I think, Trustzone and then SEV for AMD there as well. But basically what it allows is that, say, a third party like software is trying to access a service that's running in an enclave, right? Remote attestation basically allows them to verify that whether this program is actually being run in an actual enclave that's being verified by Intel, right? But then you can also have your custom like DCAP pipelines, which we'll get into later as well. Sealed storage, this is when you're basically, say like your program is running in SGX, right? And then you have some like intermediate results, right? And then you want to save that into a untrusted environment, say to your computer's own storage, like on disk, for example. And then you basically use the sealing keys here to kind of like make sure that the data that's being offloaded right into the underlying disk is actually being privacy preserved. This is a really simple kind of like description, right, of how a usual program would work when you're running this. We're running it in an enclave, right? So ECALs, which are used to enter the enclave, and the OCALs, which are used to call outside, right? The inputs of ECAL and the output of OCAL are usually not trusted. But then for an application design here, right, you can see that you have this very nice partition where you have a untrusted part of the app, right? And then you do this enclave creation process, which basically you just run these four, or I mean, the enclave would run these four commands, right, to create the enclave. And then, yeah, you do the eCall for entrance. And then there's like whenever you're interacting with like something that's outside of your enclave, right, you use the OCall command here. We'll have a much kind of like concrete example of how this would actually work in production with what we're building later. I'll go through this slide real quick, but then these are just some of the core components of your enclaves, right? So your PRM or processor reserve memory is being carved out. Your normal DRAM, right? And they also have like a enclave page cache that's being put in here, right? There's like some mappings for your cache here, right? The linear address range here is also used to basically manage your address tables with all of your pages, and then the control structure there. TCS here, it basically means that it's a piece of software within Enclave that can support like multi-threaded execution for a lot of programs. So yeah, I think there's a huge design space potentially. I mean, there's a huge design space of like whatever you can run within the enclaves, and then there are also very robust developer tooling right now that allow you to do that. Now, in the attestation part, right? So on a high level, the SGX attestations are just you're just cryptographically proving application integrity based on some of your your hardware information, right? One of the core components of that would be the TCB or trusted computing base that we're talking about, where it basically establishes an identity for the enclave. There are two types of attestations that are most commonly used, right? One is local attestation, which happens usually when you're running like two different enclaves on the same piece of hardware, right? And then you want them to establish a secure channel between the two and then do some kind of communication or like whatever, right? Say you're running an MPC or collaborative scenarios or whatever. Remote attestation is, as I was describing, where basically you have a third party, say like software or whatever, right, trying to access the code that's being run within the SGX, and then they want to make sure that the code is actually being executed in a secure enclave. Yeah, these are usually when you're having the attestation results, which you have here, right? So this is the TCP information, right? This is reported out. This is more relevant to a challenge process that we'll get into later. And then there's like some hardware info there as well. Okay, so this is what you're having for local attestation. But then before we get into that, so this is I don't know if everyone can see this picture very clearly, right? But this is the root provisioning key or the RPK what we were talking about. This is the root ceiling key or the RSK that we're talking about. Right? This one, you can see that it's used both for generating the key that's used for like attestations or provisioning, as Intel would call it. And then it's also used for like the sealing process here, right? With when you're trying to offload the data to like some underlying hardware. There's a few like transformations and then derivation algorithms that they're running to basically just KDS that they're running to get out these keys that can be used for attestation. But then for local attestation, what you're usually having is this like really neat like a challenge process, right? Say A is trying to prove to B that the program here, right, is running in the enclave, right? B would send over the MR enclave here. eReport is basically a command that allows A to generate a report or a response, right, to the particular challenge that he is sending over. And then the challenge itself is not being described here, but then you can think of that as whatever challenges you may use, for example, in the Diffie-Hellman exchange protocol. And then the response is being sent back here, right, is being verified by B, who also gets a key using the eget key command. And then, like he does this process in reverse, right? Where basically at this point, you'd have a secure communication channel being established between these two applications. This is for remote attestation. Obviously, this is like much more complicated compared to local attestation, but then the high-level idea is very similar. One of the major differences here is that, first of all, I mean, this entire process is being run in a thing called Partitioning Enclave or PVE, where you're basically provisioning against Intel servers with this particular. So whenever you're doing the attestation against Intel servers, you'd use this EPID or like enhanced privacy ID thing, which is basically used by Intel to kind of like verify that you're actually an enclave that has previously registered with them before, right? So you have EPID groups that are created based on processor types, and then there's like a anonymous signing process here to make sure that whenever people are testing here, the identity information is not directly being leaked. And then, so EPID is usually generated when you're first kind of like registering with Intel. If you haven't done this before, right, they would just like do it in the first time when you're trying to perform this process. But then I think they do have, once you have done this already, right, they have like they're basically putting, basically the idea is that you don't have to do this every time when you're trying to perform like remote attestation. Your EPID is being generated in the first time when you're trying to perform remote attestation. But this is actually, so this is actually what is causing a lot of the, I think, a lot of the attacks that, for example, the one that Andrew was previously working on, right? So Intel, the thing when you're verifying your hardware against Intel, like their attestation service or IAS here, is that Intel is usually slow in terms of like enforcing a lot of the patches for the recent hacks or side channel attacks, right, that researchers have discovered for SGX. So this basically means that even if like patches have been released outside, hardware that haven't enforced these patches can still successfully verify against IAS, right? Which basically means that, I mean, you do have like a little bit of client diversity there, right? You're not enforcing this upon everyone, but then this definitely like increases the attack surface for your application. And then, so here we're having a different set of pipelines here through ECDSA signatures. So here you're not really verifying against Intel's attestation service anymore. You're basically testing against the custom security pipelines that's being set up by, say, for example, your cloud provider, right? In this case, it can be Azure. You can even, if you're running like some servers yourself, right, you can set up like a blacklist, for example, for a list of hardware who haven't like implemented like particular patches. Here's a really neat demo of, I mean, it's not a demo, it's just a GIF of how this usually works, right? But it's very much the same as IIS. It's just that instead of interacting with IIS, you're interacting with the DCAP pipelines that you're setting up yourself. And then I always forget this, but then I think the full name for DCAP is Data Center Attestation Primitives. Yeah, this is one of the things that people rant about SGX as well, right? You know, like for the, I think the 9 slides we've been through, there's like way too many, acronyms, and then all this kind of like whatever. When you're getting to the developer tooling stuff, it's a nightmare. But yeah, sealed storage. So this is what Andrew was talking about, right? You have the sealing with MR Enclave, and then you have the sealing with some MR Signer, right? So MR Enclave is where like you're basically sealing to the exact piece of hardware there. So whenever you're doing like an upgrade, right, you need to like do like what Andrew was describing there, right? There's a bit of overhead there. So like I think in Web 2, people in general prefer to use the Enclave, the second approach, but then definitely like under a blockchain setting, this is not ideal, as Andrew was describing. But yeah, this is a seal process. See, like you have some really, like words, right? You have some really like interesting, or like not so interesting commands here. But yeah, so for the development tooling right now, we're having for SGX, right? This is the Intel official SDK. There's a C++ SDK. There's a Rust SDK. This is what we've been using. T-Club is more of a high-level computing platform in that aside from SGX, they also support like I think AMD SEV and then ARM Trust Zone. But yeah, like it's kind of like just like wrapping everything together, right? In this kind of like PaaS model, I guess, or PaaS for like us, like infrastructure as a service, where like people can just like run applications on top, right? A libOS or like SOS, right? Like this is usually if you want to run something more complicated within an enclave, right? This is what you would use. We also have a more concrete example for this later. But then the more like commonly used one is Graphene SGX. Yeah, there's a few other like Oglum, Graphene, etc. SGX Dev, this is very helpful for debugging. Andrew just recommended this to me the other day. But yeah, like a lot of, you can simulate a lot of like side channel attacks here in research. Yeah, so very, very helpful tooling. These are just like some of the common attacks against SGX here, right? For cache timing, page branch shadowing and the speculative execution, I would say actually all 5, right? They're very common in like just like normal side channel attacks against like normal CPUs, right? So SGX is just that. I think one of the reasons is that because they're trying to have this like protection against, your OS or like your VMMs with like administrative privileges, right? So whenever these happen, like the results are oftentimes even worse than you do like a speculative execution attack on a normal piece of hardware. But yeah, I think we're a bit over time here. So getting quick to what we're building identity oracles. Fundamentally, is we're bridging data from one identity layer to another. Like the first identity layer here usually is some off-chain or cross-chain data sources, right? It can be like say your behaviors on Twitter, Instagram, Spotify, etc. It can be your bank account information, can be your like your behaviors. For example, you're trying to prove your behaviors on Ethereum to like some optimism contract or whatever. And another here, like the other end of the pipeline for our oracles is basically any custom like data vehicles that's being used to host these identity information, right? It can be like on-chain, like NFTs, SPDs, your normal action trigger oracle contracts. It can be verifiable credentials within the DID system, right? It can even be like a centralized identity system. Like for example, with some Singaporean government, they have this like centralized ID system called SingPass, right? So these are all like interesting experiments we're running there. But then for this design problem itself, right, you have 4 steps. First of all, you need to authenticate someone's identity, and then this is like usually down to like, for example, parsing someone's like private credential, like OAuth, and then you retrieve the data from like that third-party server, right? Whatever third-party server, or like for example, in the case of blockchain, you'll just be like fetching that data on chain. But this is usually where you need to access like establish a TLS session to some like third-party server and do your normal like HTTPS request. And then you perform some computation, and finally you feed that into like different on-chain vehicles. Some of the primary design challenges here, right? So first of all, we have the privacy versus integrity issue, which is what exactly Andrew was talking about for CKP generation as well, right? Because you need like valid witnesses whenever you're generating these proofs. And then when your witnesses are basically private user information, or user information that can only be authenticated in a private way, it basically means that like you run into this like a privacy problem, right? If you just allow users to do this proof generation directly in their front end, then the user might tamper with data, right? I can change something before, like I can even change my HTML code before generating the proof in my browser, right? So you need to guarantee integrity here as well. But then if you do this proof generation process through like say through a centralized server, right, you're just like losing your privacy there as well, right? So that's why we have, and then there's the decentralization problem there as well, right? If like you're using a centralized server to guarantee integrity, obviously you can't have a permissionless or trustless setup for anyone to run these nodes, right? Because like everyone would be able to see like the user private information. So that's why we have designed this like modular privacy layer here, right? So on top, we have 2 types of zero-knowledge proofs that are being enabled to protect user anonymity and then user data confidentiality, right? So like for set membership proofs or your normal like inclusion proofs, right? Whether you can do that through an Merkle root accumulator, or you can do that through like a RSA accumulator, right? You have different implementations for this, but the high level idea is to decouple users like off-chain and off-chain identities. Range proofs are just used for basic like data desensitization, right? Instead of having the exact number, you're having like a range there. But then to solve this problem, right? So we have 2 different types of solutions. One is based in TEs. This is the one I'm going to dive deeper into later. So Andrew also mentioned this old paper by my professor at Duke, Fan, which is called Tonguecrier. Tonguecrier is kind of like a more general purpose, like authenticated smart contract data feed problem. It's there. We do share like similar designs there, but then for us here is more about like generating zero-knowledge truths within a secure environment where you can have both privacy and then integrity guarantee. And then the final solution there is a TLS level MPC. This is where you can run it in the front end directly, right, with a browser extension, do some WASM-based proof generation. There's a paper behind this as well called Deco. But yeah, we won't be getting too deep into that today. So Sibyl is what we are naming our TE-based like identity oracle nodes. But then the overall architecture here, right? You can see this is like the client, right? So someone is trying to fetch data from a confidential data provider, right? This usually can be, just like some third-party server here, right? And then you're establishing basically a TLS connection here with a server that's being run within a enclave. You establish the connection here. There are like some additional steps for you to like fetch the data here, do some computation here, and then like send the data back. We have a local attestation enabled here as well, right? So this is for remote attestation, right? Because whenever your client is trying to interact with the Oracle node that's being run in the enclave, I mean, Oracle node, or the TLS server, right? The TLS server that's being run in the enclave. In the enclave, you need to ensure that it's an actual enclave. But then we also have this a local attestation thing, where basically we're running a library OS within the second enclave to do the proof generation, because right now we're doing ZKP generation with Circom and Snark.js. So to efficiently run JS within SGX, we're using a second enclave. But then you can also abstract this layer out and then put that into another like server, right? And then you just do like remote attestation instead of local attestation. We support both ECDSA and the EPID attestations, right? So this would allow us to have like more custom DCAP rules against like the Intel attestation service. ORAM, which is something that Andrew and Mei-Ling are especially obsessive about. It's not super. It's not like extremely relevant to our use case, but then because we're running a HTTPS server here, right, there are like certificates that we need to protect, and then ideally to achieve like forward secrecy, right? There are some of these private keys you want to rotate whenever you're doing a new session, right? But then right now we're being lazy, so like there are keys that we're using for like 2 days or 3 days. So that's why we also have like a really simple layer of ORAM there. It's just like the most, I think, basic square root ORAM, which is a paper proposed like back in like 1980s or something. Yeah, like 20 years before I was born. So it might not be super robust in these days. But yeah, like this is like the proof generation is being done here, right? Within the libOS, and then we also have like the server set up with some non-blocking IO. This is a really cool Rust library, MIO. I was used to it, like enable, just like in general non-blocking IOs. But yeah, so I know we're running out of time, so a brief kind of like rundown of how the Handshake process works, right? So the clients, this is just a normal TLS connection, but then there are elements for remote attestation that's being integrated here. Do this like interaction with the server, would generate a key pair for signature. The code that's being produced here from the coding enclave, this is basically what Intel is calling their reports whenever they're doing like remote attestations, right? And then you do like IAS, or like you attest through like IAS or like DCAP, right? To make sure that the server is actually running in an enclave, right? And the report is being concatenated into the certificates that's being sent back to our client, and the client would verify basically Intel root CA, right? It would verify the attestation report, and then it would also get the public key for the attestation report. And then this is where when the client, like basically you're done with the handshake phase, right? This is like in a normal like TL session, you first go through the handshake phase, and then you do the actual query, right? So here you're just like, for example, here we're just like trying to query whether a user has a balance in a bank that's, for example, within this particular range, right? Because we're doing like a ZK range proof here, right? So send the query request here, right? And then the server, like the enclave, would check the query and then construct the full request body, and then send the relevant credentials here, right? It's responded, and then we would have the ZK range proof being generated here, and then a code is being produced from the enclave alongside the for the report data that's going to be sent back to the client as a part of the attestation. And then here, like, you need to do the attestation generation, and then finally, it just goes back to the client. I also have a really short demo here as well. Let me quickly show that. So can you scroll? This is the query we're constructing here, and you can see these are results, or the attestations. There's a few like different signing keys here. Right? This is the signing keys that's corresponding to the certificate for the enclave for the server that's running in the enclave, and the other signature is created by the private keys that's generated per session, right? The one I was talking about. To like ideally we need to rotate that per session for secrecy. But yeah, this is pretty much it for the entire presentation. I know there's a lot of things that we're packed into here. Let me get to this here. So slides, you can scan this, right? And then on Twitter, yeah, I mean, just like showing our company for like 30 seconds, Andrew, please. But yeah. So on Twitter, I'm a dolphin. This is my Twitter. Click. We're the second. We have the second highest DAU on Optimism. Check our company out as well. We're doing some cool stuff. And then yeah, slide you can scan for here. There's much more information that's packed in the speaker notes that I didn't have the chance, the time to go through. And this is my paragraph. Yeah.
First of all, yes, is your code open source at all? Like to have Circon and even like SGX? That's really cool.
Yeah, it is. Dude, I invited you to a repo.
Well, that's not the same as being open.
No, it's not fully open source. Yeah, we're still doing like tests and all that.
With ECAP, I've been trying to figure this out. Like, when you do our own ECAP, do you have to trust the ECAP thing, or it's just a cache? It's not really like structured.
I feel like it's more the former compared to the yeah. But I mean, if you're running on Azure, it's easier because they have their like I think DC v3 and then DC v2, like they have like different. I think so. One of the two only supports IAS, but then the other like you have the. Actually, it's not IAS. One of them only support the decap that in Azure, so Microsoft is running, and the other where you can have like more customizability where you can set up your own decap rules as well. Yeah. But I mean, right now we're just using that to like, have a blacklist of like hardware. So good questions.